did not access the test over the weekend, please make sure you talk to me at the end of class. Otherwise, I'm gonna start sharing my screen, and I want to hold off on looking at any test questions that anybody might have been asking about until after I get the papers graded. Realize that if you submitted your work in Blackboard, once I've graded it, you should be able to look and see what I marked right or wrong. I only got a chance to grade a couple of papers, and sadly, the ones that were wrong had no work for them, so it's tough to give you partial credit for that. Does anybody have any questions on any of the homework problems before we begin? If not, I think you can see that what's coming up next are functions, homework 2.1, which is on the definitions of functions, will be due on the 26th, which will be Friday. And we're not looking at section 2.2, but homework 2.3 will then be due a week from today. And Carissa, we got that you came in. So let's start by looking at functions. But before we look at a function, there's another term that we have to define, and that's a relation. And we're going to define a relation as a set of ordered pairs. And so a relation can be any set of ordered pairs. They can be numeric, or they can be otherwise. So an example of a non-numeric relation might be if I look at something like a class roster. And if I look at a class roster, I might consider it a set of ordered pairs where I have people's last names and then their first name. And so I could have this roster, when I call attendance every class, that would be a relation, a set of ordered pairs. When we talk about a relation, we talk about two different sets within the relation. One is that of the domain, and I'm skipping a little space. The other is that of the range. When I talk about the domain of a relation, it's the set of the first members of each pair. So in the above example, the domain would be the set of last names. That's an N, by the way. And the range would be the set of second members of each pair. So in the example with the class roster, the range would be the set of first names. So if I look at a relation as being a set of ordered pairs, the first members are the domain, the second members are the range. Sometimes when people think of the first members, they think of them as being the X values. And when they think of the second members, they think of them being the Y values. And that idea to a certain extent, helps me remember which is the domain and which is the range. When I look at a set of ordered pairs, I look at them as X, Y, and I remember that X comes before Y because I put them in alphabetical order. So if I look at the words domain and range, if I put them in alphabetical order, domain comes first. So the domain are the first members, range comes second, the range are the second members. And so I could have a relation, something like my class roster, pairing last names with first names. We're going to look. Question? We're going to look more at number sets. So let's look at another example. Let's say I have a set S that contains the ordered pairs 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4. And so we're pairing some of the integers with their squares. For this relation, what would you tell me the domain is? What would be the set of first members? The 1, the 2, the 3, the negative 1, and the negative 2. And instead, if I looked at the range would be the set of the Y values. So those would be 1, 4, 9. 1's in there already, so we're not going to repeat it in our set. And 4's in there already, so we're not going to repeat it in our set. So our range are the numbers 1, 4, and 9. If I look at, well, let's stop here and now define a function. And a function is a relation. So it's a set of ordered pairs, but this is a very special type of relation. It's a relation in which each member of the domain is paired with one and only one member of the range. And so each member of the domain, well, that's each X value is paired with one and only one member of the range, or that's saying that each X value has only one Y value. It's kind of the idea that the X values cannot repeat. They cannot be used more than once. And so if I look up at S, when X is positive 1, it's only paired with positive 1. When X is positive 2, it's only paired with positive 4. When X is positive 3, it's only paired with 9. Negative 1 has only one partner. Negative 2 has only one partner. So in the example above, is S a function? And the answer would be yes. Each X value appears only once. So let's look at some more examples. let's have T be the set of ordered pairs. 1, 3, 2, 4, 3, 5, and 4, 6. And I'd like to ask you folks to please for me find the domain of T. Sometimes you see D for domain in that subscripted T. The range of T, and that would be R with a subscript of T. And I want to know, is it a function? So what's in the domain of T? For those ordered pairs, what would you tell me the X values are?
One, two, three, 4.
Beautiful. What's the range? What are the Y values?
3 to 6.
3, 4, 5, 6. And is it a function?
Yes.
Yes, each value occurs only once. Let's look at another example. This time, let's have V be the set of ordered pairs. 5, 2, 6, 2, 7, 2. I want to know the domain of V, the range of V, and I want to know if V is a function. Is everybody getting the domain? The X values are 5, 6, 7. The range, the Y values, they're all 2. So there's only one element of the range, 2. And if I ask if it's a function, if I notice each X value occurs only once, so yes, it is a function. Next example, let's look at W. And this time, let's pair numbers with their square roots. So I could have 1 with 1. I could have 1 with -1. I could have 4 with 2. And I could have 4 with -2. And we want the domain of W, the range of W, and we want to know, is this one a function? And is everybody getting the here? The domain, the X values are just 1 and 4. The range, the Y values are 1, -1, 2, and -2. And this time, if it's a function, I'm going to say no, because if you look, 1 occurs twice. 1 is paired with +1 and -1. Likewise, 4 appears twice. And so 4 is paired with 2 different members of the range. So it's not a function. Everybody all right with that? Any questions?
Nope.
Then sometimes a function can be given by an equation. And I might have something like x plus y is equal to 7. We could think of this as y is equal to 7 minus x. X is then considered my independent variable. I pick my x, and then I find out the corresponding y. So y is considered the dependent variable. And so usually when we're looking at a function, we want to solve for y. And this is a function because any number I put in for x, I will only get one corresponding y value. So it is a function. Another example. Let's say I have something like x squared plus y equals 25. And if I go through and solve for y, I get y equals 25 minus x squared. And this is a function because any value that I put in for x will only give me one y. Next example, I'm going to switch that one up a little bit. And I'm going to say that x plus y squared equals 25. And now this time, when I solve for y, I get y squared is equal to 25 minus x. And then to fully solve for y, I take the square root of both sides, remembering that every expression has two roots, a positive and a negative. And so I get y equals plus or minus the square root of 25 minus x squared. I'm sorry, not x squared, x, I apologize. And you notice that this one's not a function because for any x value, I can get two y values. And so can everybody see the difference between these last two examples? Not hearing any concerns then? Let's next look at what's called function notation. And it's another way of writing of functions. When I look at a function, sometimes functions are frequently named. We'll look at the end of the semester at our trig functions, which have very clearly defined names like sine, cosine, and tangent. But other times, functions are named sometimes using lowercase letters. lot of times for a function, you see an f. So let's say, for example, we have this function f, and f is the function y equals 4x plus 5. With function notation, I'm going to say that f followed by x with parentheses is y. This is read as f of x, and f of x is just another way of writing y. And so where we have f as the function, where y is equal to 4x plus 5, we could have written that as f of x equals 4x plus 5. And this is just another way of writing y equals 4x plus 5. Function notation, though, is frequently used to help us when we actually substitute in values for the variable. So for example, I want to look at a problem. Let's say if y equals 4x plus 5, I want to do this two ways, one on the right-hand side and one on the left-hand side. I might ask you to find y when x is some number, let's say 2. And so what would we do? We'd say y equals 4 times, we'd substitute that value in for x and work it out, and we'd get y equals 13. So we would be able to say that when x is 2, y is 13. We could say we've got this ordered pair 2, 13. Instead, we could have written that as if f of x equals 4x plus 5. Over here, when we're saying we want to find the y value when x is 2, we're substituting the 2 for the x. So we might instead have written that as find f of 2. And what this means is to find y when x equals 2. We've substituted the 2 in place of the x. So f of 2 would be 4 times 2 plus 5. Or we'd say that f of 2 equals 13, which is like saying when x equals 2, y equals 13, or we've got the point 213. So that function notation, if we've got our function or relation defined that way, whatever goes inside the parentheses that gets substituted for x. And you're going to find quite a few in the homework that deal with this notation. So let's look at another example. This time, let's say f of x is 3x minus 6, and we want to find each of the following. And so I want to find f of negative 4. I want to find f of x plus 1. I want to find f of negative x. And then let's also find f of 7. when I look at a function in this form, I kind of look at x as a placeholder. And so I see it as f of whatever goes in the parentheses is what I put in place of my variable x. So if f of x is 3x minus 4, f of negative 4 would be 3 times, well, I'm replacing x with negative 4. So that would give me negative 12 minus 6, or negative 18. Sometimes with function notation, we substitute a variable expression. F of whatever in the parentheses is 3 times that quantity minus 6. But what's in the parentheses this time is an expression x plus 1. And so now I can simplify that. That would give me 3x plus 3 minus 6. And so I'd get 3x minus 3 as my final answer. F of negative x, well, what's in the parentheses takes the place of x. So this time I'm replacing x with negative x. Excuse me, I'm sorry. And so simplifying that would give me negative 3x minus 6. And if I have f of 7, that would be, again, the rule is 3 times what's in the parentheses. What's in the parentheses is 7, so that's 3 times 7 minus 6, or 21 minus 6 would give me 15. How is that? Let's have you folks try another one. This time, let's say g of x is x squared plus 2x plus 1. We want to find g of 2. Let's find g of negative 2. Let's find g of negative x. And let's find g of x plus 1. And I'm going to be quiet for a minute and ask you folks to do that substitution. How did I do? Did everybody else get that g of 2 is 9, g of negative 2 is 1. G of negative x is x squared minus 2x plus 1. And g of x plus 1, well, that would be x plus 1 quantity squared plus 2 times x plus 1 plus 1, which simplifies to x squared plus 4x plus 4. Everybody okay or no? Any questions?
Nope.
If not, then sometimes we're asked to find the domain of a function given by an equation. And sometimes they specify what the domain is. They tell us what to use for x. But if they don't tell us, if it's not specified, it's going to be all real numbers for which the expression is defined. It is all real numbers for which the expression is defined. All values for which the expression is defined. Well, that's a lot to wrap your mind around because most things are defined for every value. There are only 2 things that you have to watch out for, 2 things that are not defined. And so if I'm looking for the domain of a function that's given by a rule, what I look for is the 2 things that are undefined. And so what's undefined? Well, we've looked at 2 things. We can't have a 0 in the denominator. And if we're restricting our thought process to real numbers, we can't have a negative radicand. If we have an even index. So if I'm looking for a function, it's like in the preceding problems where we had to find what values to exclude. So to find the domain of a function, it'll be all real numbers, except we have to exclude values that give you a 0 denominator. And we have to exclude values that give you a negative radicand. If the index is even. So I'm guessing that you're wondering what that's all about. So let's look at some examples. Let's find the domain of each of the following. And first of all, let's have f of x equals x plus 2 over 3x minus 9. Because it's a fraction, I have to exclude what makes the denominator equal to 0. And we've done this before. When I set that denominator equal to 0, I get x equals 3. So here the domain would be all numbers except 3. Or we could write it as x cannot equal 3. Or we could write it as all of the numbers less than 3 combined with all of the numbers greater than 3. All three statements say the same. Say the same thing. Oh boy. Instead, if I have something like g of x equals the square root of, let's not use 3, let's say 2x minus 12, because I have a radical, I have to exclude where the radicand is negative. And so what I'm going to do is I'm going to say that what's underneath the radical, that 2x minus 12, if it can't be negative, it has to be greater than or equal to 0. And so solving this, adding, I get 2x is greater than or equal to 12. And dividing, I get x is greater than or equal to 6. So the domain can be written as x must be greater than or equal to 6, or we can put that also in interval notation, all of the values greater than or equal to 6. One last example, if I have h of x equals 5x minus 12, does everybody notice that this one has no fraction? So I don't have to worry about a 0 in the denominator. And this one has no radical. So I don't have to worry about taking the square root of a negative number. And so the domain, there's nothing to watch out for. So it will be all real numbers. Or we can think of it as the interval from negative infinity to infinity. And so if we're given numbers to use for x, that's our domain. If we're not given numbers to use for x, and we're giving a rule, an equation to define a function, to find the domain, we have to watch out for two things. If it's a fraction, and we already know that that denominator can't be 0, or if it's a radical, because we're going to be restricting our thought process to real numbers, what's underneath that square root symbol cannot be negative if I have an even index. Everybody all right? Not hearing any questions then, the next thing we're going to talk about is the graph of a function.
ma'am, please, I wasn't done with the last.
I'm sorry, what is you, Azim?
I wasn't done with the last.
You
Yeah.
want- Let me know when you're done.
Okay. Yeah, I'm done.
Okay, great. The graph of a function is the set of points whose ordered pairs satisfy the function. And so we might have something like this. And for this diagram, we might be asked to find the domain, the range, and then we might be asked, is it a function? And so in looking at something like this, hopefully everybody's comfortable reading their coordinates. This would be the point 1, 1. This would be the point 2, 1. This would be the point 2, 2. And this would be the point 3, 2. And so the domain would be the x values of those points, 1, 2, 3. The range would be the y values of those points, 1 and 2. And is this a function? Is each x value used only once? Any ideas?
No.
No. No, it's not, because if I look over here, when x is 2, it's paired with 1. And when x is 2, it's also paired with 2. And so that takes us something that's called the vertical line test. And what the vertical line test says is that a graph is that of a function if and only if any vertical line intersects it at most one point. And so if I look at that graph that we just drew, if I picture a vertical line, let's make the vertical line green. Over here, my vertical line would pass, I'm only hitting one point. Over here, my vertical line would pass, I'm not hitting anywhere. But over here, my vertical line would hit 2 points. And so over here, it would fail the vertical line test. So it's not a function. And so sometimes it's easiest to tell if a graph represents a function, of if something is a function, pardon me, if I look at its graph. So for example, I'm wondering, is each graph that of a function? And let's say I have on my graph a slant line. And over here with my slant line, if I picture trying to draw in all sorts of different vertical lines, I'll do them with this highlighter. You notice how each vertical line only crosses it in one place. So here my answer would be yes. Instead, something that we'll look at a little later, if my graph is a circle, if I draw in my vertical line, that vertical line crosses it in two places. So my answer would be no. Instead, I think earlier in the semester, we looked at the graph of an absolute value relation, and we had this V shape. And if I picture any vertical line, it will only cross it once. So this would be a function. Sometimes, and now I have to apologize, I don't remember if there are any of these in the textbook or not, but sometimes you see something that's called a step function, and it's called a step function because it looks like a set of stairs. And so we'll have this endpoint filled in, but then we'll have this endpoint open. And this one's filled in, and this one's open. And this one's filled in, and this one's open. And as I look at this, the only place that would be questionable would be where those endpoints overlap. And because this one's included, but this one is not, this would be a function. Two more. We'll be graphing shapes that look like this a little bit later. It's called a parabola. And we can have a parabola that opens this vertically, or we can have a parabola that opens horizontally. And if I picture my vertical line test, does everybody see that this first one that opens upward is a function? But instead, if I look at this second one that opens sideways, my vertical line crosses twice. So this one is not a function. And so the idea of how to use function notation, how to look at a graph and determine if that is a function or not, and how to look at a graph and find its domain and range. All right. Hearing no questions, the next thing that we're going to look at then are the intercepts of a graph. And the intercepts are where the graph crosses the axes. And so I'm going to draw a set of axes. And let's first talk about what an x-intercept would be. An x-intercept would be a place where the graph crosses the x-axis. So it has to be a point on the x-axis. And so as I look at all of these points on my x-axis, what they all would have in common is a y value of 0. So the x-intercept is always of the form. It'll have some x value, we'll call it a, and its y value will be 0. And so to find an x-intercept, we'll substitute y equals 0 and solve for x. Instead, if I want my y-intercept, my y-intercept is going to be a point on the y-axis. And because it's on the y-axis, its x value is 0. So the y-intercept is a point of the form. The x value is 0, and there's some y value, we'll call it b. So to find the y-intercept, we'll substitute x equals 0 and solve for y. So let's look at a couple of examples. Let's find the intercepts for each. And let's start with 3x plus 4y equals 12. And to find the x-intercept, we'll have y equal to 0, which gives us 3x plus 4 times 0 equals 12, or 3x equals 12, or x equals 4. So my x-intercept is the point 4, 0. Instead, if I want my y-intercept, I'm going to put in 0 for x. So that becomes 3 times x is 0 plus 4y equals 12, which would simplify to 4y equals 12, which would give me y equals 3. And so my y-intercept is the point 0, 3. Let's look at one more example. Let's look at x squared plus y squared equals 81. And let's first find our x-intercepts. And for that x-intercept, we said we'd substitute y equals 0, giving me x squared plus 0 squared equals 81, which would give me x squared equals 81. But remember, when I take the square root, I have 2 square roots of 81. So it could be 9 or negative 9. So this would have 2 x-intercepts. They'd be the point 9, 0, and the point negative 9, 0. And in the same way, with this equation for my y-intercept, again, if I'm looking for the y-intercept, I'm going to substitute in 0 for x. And so that would give me x is 0 squared plus y squared equals 81, which would give me y squared equals 81. And when I take the square root, again, I have to remember 81 has 2 square roots, a positive and a negative. So that could also be 9 or negative 9. And so my y-intercepts are points with an x value of 0 and a y value of 9. And then there's another one with an x value of 0 and a y value of negative 9. And so to find our intercepts, if the graph's right in front of us, we can just look for the points where it crosses the axis. If the graph is not in front of us, we're going to substitute 0 for the other variable to find the intercept. Everybody all right with that? Any questions? If not, a goodly portion of this unit we're just starting is going to deal with linear functions. And a linear function is going to be a first degree equation, which again means it only has exponents of 1 in 2 variables. Mr. Blitzer refers to the general form as ax plus by plus c equals 0. So if it's in general form, one side is 0, a, b, and c are real numbers. So an example might be something like 4x plus y plus 13 equals 0. And I'm talking to a room full of intelligent college students. Can anybody guess why these are called linear functions?
Does they create lines?
Yep. The graph of a linear function is a straight line. And so section 2.1 deals with what makes something a function or not and finding the domain and range of a function. 2.3 spends a lot of time looking at these linear ones and looking at their graphs. And we're going to find that there are several ways that we can use to graph a line. And I think the first one is the method that we use for graphing. I think there was a question asking us to graph this way on that last test. So to graph a line, one thing that we can do is we can make a table of values. So for example, if I ask you to sketch something like 2x plus y equals 6, usually when I make a table of values, I like to use 3 values. Most often people substitute for x to find y. And with my 3 values, I like to use a positive, a negative, and most often 0 is a nice number to substitute. And so I'm going to make my table, put in x, find y. 2x plus y equals 6. Let's use 0. For a positive number, let's use 1. For a negative number, let's use -1. And so if x is 0, 2 times 0 plus y equals 6. I apologize, I should have left a little bit more room between these. Gives me y equals 6. And so 1 point will be the 0.06. When x is 1, I get 2 times 1 plus y equals 6. Well, if 2 plus y equals 6, y would be 4. And if x is -1, I'll have 2 times -1 plus y equals 6. Or -2 plus y is 6, which would give me y equals 8. And then I'll go through and plot my points. And so I've got 0, 6, 1, 4, -1, 8. And I'll connect them with a straight line. So is everybody comfortable with graphing an equation by making a table of values? If so, when we talk about a line, one quality of a line that we frequently discuss is the slope of a line. And the slope of a line is a measure of the slant of the line. And so when I talk about the slope, it tells me how steep a line is. Frequently, slope is represented by a lowercase m. And when I talk about how steep something is, something comparable is if you have a house and you have a roof done, they talk about the pitch of the roof, how steep it is. And it's a ratio. It's a ratio of the rise over the run, how much it goes up over this horizontal distance. And so the rise going up and down is the change in the y direction. The run, the horizontal movement, is the change in the x direction. Sometimes, because mathematicians are intrinsically lazy, they don't like writing words. Sometimes you see this symbol here. It looks like a triangle. It's a Greek letter delta, and it's used to represent change. And so the change in y is sometimes delta y over the change in x is sometimes delta x. But when I measure change, change is sometimes also referred to as the difference. So that change in y would be the difference in y values, and the change in x would be the difference in x values. When we look at this, we sometimes find the slope between 2 points. And so some people look at it as a formula. So we have these 2 points, xy, xy. The problem is when I write them like this, it looks like the 2 points are the same point. And so sometimes you see subscripts x1, y1, where those subscripts tell me, okay, that's my first point. And then over here, x2, y2, that would be my second point. I guess if you're given 2 points, it's arbitrary. It's up to you which you consider your first and which you consider your second. But when I look for how the y values change, to find that change, I subtract. So it would be y2 minus y1, the difference in the y values. And then in the denominator, the change in x would be the difference in the x values, x2 minus x1. When I look at this formula, again, it's arbitrary, which is your first point and which is your second point. But once you declare that, you have to be consistent so that these should be from one point and these should be from the other point. And so let's say, for example, in the line above that we just graphed, I think 2 points that we had were 0, 6. And the other point that we had was 1, 4. If I want to find the slope between them, my slope formula is the difference in the y's over the difference in the x's. And again, it's arbitrary which of these you use as your first point and which of these you use as your second point. I guess this will be my x1, y1, x2, y2. And so 4 minus 6 over 1 minus 0 would give me -2 over 1, or -2. And if I look at that idea of the slope being negative, I want to scooch up to that graph that we made. And this has a negative slope. As I look at it from left to right, do you see how my line is decreasing? So over here, our slope was -2. Our line decreases or goes down as I look at it from left to right. And sometimes if I have a graph in front of me, in order to find the slope, rather than pulling that formula out, I almost count blocks when I go from one point to the other. Do you see how I go down 2 over 1? So that would give me the slope -2 over 1. I just want to write one more sentence and then we'll call it a day. A negative slope is a decreasing line. The line goes downhill as we look at it from left to right. So we've covered kind of a lot of territory today. Have you folks seen that slope before? Have you folks graphed lines making a table of values before? And is everybody all right with that definition that we have of a function? Now, a few of you came in after I took attendance. Let me just tweak the attendance a little bit. Tom, you were here already. You must have gotten booted out. Rizwana, I added you.
Thank you.
Aziz, I added you. Is there anybody else who came in late? Dekea, let me add you. And who just said I did?
Mike Brown.
Okay, yeah, you came in just as I finished taking attendance, so I do believe that I got you, Michael. Let me just scroll up and see. Yeah, okay. So we'll see you guys on Wednesday.
Did you get me?
Yeah, Decay, I just did. Thank you.
You're welcome.
Okay. Michael W., your power went out? You lost your internet?
Yeah, I tried to sign on Friday and then all of a sudden it just went to page not found, and my friend came over last night and finally got it working again.
Can you get that test done by the end of the day today?
Yeah.
And so I am real quick going into my labs on my Chromebook, and I don't want to stop talking to you until I get this done because I'll get distracted and forget to do it if you don't mind waiting.
Yeah, that's fine.
And so I'm going to go to Michael W. and I'm going to go to test 2. And I'm going to go to settings per student. And I'm going to use individual setting and give you until 11:59 tonight.
All right, thank you.
Just when you go into my labs, you might want to refresh it to see that that was done. Okay.
Okay.
All right.
All right, thank you.
Keep on. Bye-bye.
I also came in late, Taylor.
Okay, Taylor, I'm sorry.
And I had a
Right.
question about the test. I did not see the exam in math labs. Oh, that's not a that. Oh my God, excuse me. I did not see the test in my math labs that I do not have access to. I ain't see it there.
You, do me a favor. Are you on your computer now?
I can't.
Yeah, boot it up. And I need a second to get you in attendance before I go back into my labs. Okay, we've got that you're in class now. Okay, when you go into my labs in Blackboard,
Okay.
click on just first my labs, and you've got that page in Blackboard. In Blackboard. I want you to click on, well, even if you click on all assignments, the test should show.
All right.
It test 1, yeah, test 2 is in there. It wasn't available until after class time on Friday. But do you see it there now?
Hold on, I'm still logging into my Blackboard. I'm in here now. Let's go to the class. All right. So I went to the home page. Where you want me to go click again? Learn.
In my labs, if you're in the home page, you're going to click on quizzes and tests. Are you in the home page for Blackboard or for my labs?
Blackboard. I don't got my labs.
Okay.
I don't got access to that.
You don't have access to my labs?
No, I usually do it on paper and get it through my learning module, and it usually be at the bottom, which it wasn't, and I didn't want to.
Oh no, it's in. I'm sorry, I thought you had gotten my labs. I
Oh,
thought
no,
you
no,
had
no,
gotten my labs. Didn't you get my labs?
Mm-mm. I didn't have that.
Okay.
I still didn't have it.
I apologize. Then if you go to learning modules and content, it says if you do not have my labs access.
Yes, I'm here right now, and it go up to homework 1.1, 2, 3, 4, 5, 7, PS2, homework 2.1, 2, 3, 2, 4, 2, 8, and then homework 3.1. And I don't see no quiz or exam or anything.
Let me just double check something. I have to apologize.
No, you fine.
It could be that I will make sure that it's in there. Can you get it done today?
Oh yeah, absolutely. I just did not want to get a 0 for it or anything.
No, you shouldn't get a 0 for it. And I guess you're going to do it, and then you're going to submit your work in the Dropbox for submit your work. Let me just look one more place.
Okay.
I put it in the wrong spot. I could have sworn that I put that test in there. I apologize. It'll be in there as soon as I get out of Zoom with you. All right.
Okay. Thank you.
Okay. Sorry about that.
No, you're fine.
All right.
Have a
Bye-bye.
nice day. Bye.
You too.